Symmetry, very important topic, symmetry. Physicists love symmetry, okay? If you ask them why, they'll give you some bullshit about the beauty of the universe and the nature of this and that's really not true. The real reason is that we're lazy and it makes problems easier to solve. So let's start with a good, simple definition of symmetry. When an object looks the same on both sides of an axis. Okay? When an object looks the same on both sides of an axis. So let's think about our charged rod problem that we just did. Here it was. It's a nice charged rod, charge density lambda. And the key was that this point that we were trying to figure out, the E field, was along the center of the rod. Remember, it was at 0, and we had a length L over 2 here, and a length minus L over 2 there. So this was a symmetric problem because along the axis that we cared about, the axis along which we were calculating the electric field, we had the same length of rod. It looks the same this way, and it looks the same this way. So by this simple definition, it was symmetric. Okay? So you say, so what? It was symmetric. Why are we excited? We're excited because of the lazy part. Let's add to our definition. We can use it to predict when something equals 0. Okay? We went into this problem and we thought about DEP and we calculated all the components, we did all these integrals, and it was a long problem. Half the difficulty was doing the x-axis and half was doing the y-axis. But let's think about it. If we had thought about symmetry, we might have realized that here is a dx right here. This dx is going to make a DEP like that. But what about the symmetric dx, the one over here? It's going to make a DEP like that. And they're also symmetric. The two DEPs look the same on both sides of the axis. But what about their x components? Their x components look like that, and if you add those as vectors, they cancel. So the two symmetric dx's will have canceling x components of the DEP. And you could say, well, what about this dx way out here on the end? It also has a symmetric dx. It would create a field, DEP kind of like that, and a DEP kind of like that, and its x-axis component would be that, its x component would be that. Any dx you come up with on one side has a dx on the other side that is symmetric. They make symmetric vectors, and the x-axis always cancels. So basically, by symmetry, we could have known ahead of time that, that EP is going to have a 0 on the I hat. And then we would still have to solve the J hat. So the problem could have been 50% easier. We could have just completely ignored the x hat without even starting, just by looking at it and saying, oh, well, it's symmetric. Don't worry about the x component. Okay? Another example then, let's think about this. Let's think about a ring of charge. Let's do a problem really fast with symmetry. Okay? Here's a circle, and it's basically a rod of charge that has been bent into a circle. It's got a charge density lambda going around the circle. So the total charge would just be lambda times the circumference. The question is, let's calculate the E field at the center. Okay? What is EP? Well, you can imagine we could break it up into little dx's going around. We could write Coulomb's law. We could do all these integrals. We could do all this stuff, but there's really no point because I know that it's going to be 0 by symmetry. Because for every dE or every dx here that has some q, some charge, dq, that's going to create a field that way, and there's a symmetric one here that's going to create a field that way, and the two are going to cancel. For every one here that creates a field that way, there's going to be one here that creates a field that way, and the charges are going to cancel, or the fields are going to cancel. So you can instantly say that the E field in the middle is 0 because you're at a point with a certain symmetry. Okay? It doesn't always make everything 0. Right? You can't just say symmetry 0. You got to think a little bit about how it makes something 0. Another way to think about it is you can think about explicitly about all the little dx's and dq's making vectors and what adds up. Another way to think about it is something is 0 when there's no way to know which way it would point. Okay? So if you looked at this point and thought, which one is going to be 0, it has to be the x component because there's no reason that the x component would point left or right. Okay? Is the E field going to be to the right or is it going to be to the left? Well, there's nothing special about right or left. Right and left are the same. Therefore, that's the part that's 0. Here, is the E field going to be up or down or right or left? In this case, no direction is special. Whenever a direction is not special, that's the one that's going to be 0. Okay? So symmetry, they can't give you a mathematical law of how to use it for this class, but you can definitely use it to make problems easier and speed them up. Okay? And it can save you a lot of time. Had we made one little mistake calculating EX, we would not have gotten 0. And we would have got the problem wrong. So it would have been much more efficient and safe to simply say it's 0 by symmetry. Another way you can use symmetry is to break it. You just got it. Like a cheap toy, let's break it within minutes. Okay? These are the kinds of problems with broken symmetry we can use to help you think about symmetry, like on the homework. For instance, here's a ring of charge with a little piece missing. So without doing any calculations, you could say, which way is the field at point P in the center? You don't have to do any calculations to know that it's this way. Okay? Because you can think about all these dx's canceling. The one that doesn't have anything to cancel is right here. So as long as the charge is positive on the ring, the field would have to be that way. All the other components will have their things cancel. But this component here is missing its partner over there. So E is going to be to the right. Okay? That's an example of broken symmetry. Another case of broken symmetry is we could do the rod and not put the point at the center. Okay? This is another key thing to realize. The rod is very symmetric in and of itself. You can draw an axis of symmetry through the rod like this. That's a symmetric axis for the rod. You can draw an axis of symmetry here. That's a symmetric axis for the rod. But it has to be the axis you're using in the problem. If you put your point P here, there's really no axis you can draw that's symmetric. You're probably going to do the problem like this and think about these dx's and these dx's. And then you're not on an axis of symmetry, so nothing's going to be 0. The x component is not 0. The y component is not 0. You could kind of look at it and we could ask, is the field going to point more or less to the right or the left? Just worrying about the x component. And in this case, you look at it and say, well, there's more on this side than that side, so it's going to point. Something like that. Okay? So use symmetry to make hard problems easier and use it to think about the direction of a field. We'll use it for many more things later, but that's your introduction just to start thinking about symmetry.